Alrighty, let's make a start. So, for today's lesson, the main focus of the lecture portion is going to be on basically introducing this idea of differentiation by first principles. And so essentially we're going to start by building up some of the foundational elements of how differentiation essentially came to be. And so one of the key concepts we'll have a look at will be around this idea of limits. We won't go all the way into continuity. That'll be for a different section. We only need to learn as much limits as it takes to then apply that to differentiation by first principles. So overall, it'll be a fairly short lecture portion. We'll have a therefore longer Q&A section, essentially. So let's begin. What is a limit? So the idea of a limit essentially came about to sort of attempt to figure out what's happening to functions at weird spots on their graph. Now, the typical example I'll give here will be any discontinuities or any asymptotes, right? Stuff like the hyperbola, for instance. What happens when x equals 0, right? Exploring what's going on there. That's where limits are typically used. However, technically speaking, a limit can be used for any function, and what you essentially do is a two-stage approach. What you do is you pick the x value that you want to identify the behavior of. So in this example, we're checking out x equals 0, right? That turning point of the hyperbola. Step 2 is then identifying or observing the y values as approached from the right, as they get closer and closer to that particular x value. The exact same thing as approached from the left, right? And so the idea is that you want to look from both sides of the function, converge on a particular x value that you care about, and then whatever result you converge onto is the limit of that function. So in this case, the limit would be 0, because whether you come from the right or from the left, the y value to get closer and closer to is 0. Now, a more useful example for limits would be something like the hyperbola. Although in this particular example, we're not going to come to anything conclusive. If you come from the right-hand side, you'll notice the y values approach positive infinity, right? That'll shoot up and up and up forever. Whereas from the left-hand side, they'll shoot down forever, down towards negative infinity. For the limit to exist, where it converges needs to be identical as from the left, as also seen from the right. In this case, they diverge. They go in two completely separate locations, and for that reason, limit does not exist. Worth pointing out a few nuances about that. If I draw a truncus, for instance, just to highlight what that would look like, you might be inclined in saying that the limit does potentially exist, because when you come from the left-hand side or the right-hand side, both of those are shooting off to positive infinity. The nuance there is that infinity isn't a number. And so for that reason, even though they're converging in the same direction, they don't converge to a particular value. And so for that reason, we still say the limit does not exist for that particular function. Fair enough so far. Is there anything I should clarify about that?
Chris, does that mean something like as you said, like a trunk is that doesn't have a limit?
Yeah,
Like,
correct. Well, the limit does not exist. Now, one thing that's probably worth pointing out maybe now is how that appears on a CAS. So if I go ahead and do exactly what I just did there, it's in the menu for the TI Inspire limit, the notation will be something like this. As x approaches 0, and you'd have your 1 over x squared to make it the truncus. It's going to say infinity. Now, mathematically speaking, when you give your answer, yes, you can say infinity, but a more accurate answer is to say limit does not exist. That's whenever you have a non-number as your result, that's the criteria for limit does not exist. This is me just sort of warning you. CAS won't say does not exist. CAS will put some infinity. It might even put a negative infinity. Like for instance, if I put a negative sign on this, it'll make it negative infinity. Not so good. So we say does not exist. Cool. Okay. The only thing that we really need to know for limits is going to be how we solve them by hand or technically by CAS, although by CAS it kind of just does itself, so we don't really need to focus too much on that. You just obviously plug in the values and then you get your limit. So if you refer back to the screen share, we'll have an example of how we handle these, what are referred to as discrete limits, which is limits that are approaching a very specific x value. As I said at the beginning of the lecture, we pretty much only use limits where the function has a weird spot on it. Something that would cause an asymptote, something that would be undefined. In this case, we have an undefined spot on the graph, because if we were to directly sub in x equals 2 into the function, we have a divide by 0 error. And so for that reason, we have to do a bit of pre-processing to make it work out. Fundamentally, all we're ever doing is changing up what's in the numerator to eventually cancel out what's in the denominator. In this particular circumstance, and in a lot of circumstances when you're just doing limit stuff, a lot of the time you're just factorizing. If you factorize your numerator, you will see that there's both an x minus 2 in the top and bottom of the function, and so for that reason they can cancel out, and it's now that you've removed the discontinuity, they are called a so-called removable discontinuity. When you sub in x equals 2, you no longer have that divide by 0 error. Now, that's how you evaluate limits. As for what's actually just happened here, I'll demonstrate on the CAS. So if we go to the handwritten section, and for Katami, just real quick, we've got a couple of different screens here. One is for any handwritten notes that I do. One camera's pointing at the CAS, the other's for a screen share. So just like maybe ping me or hop off mute if you're having trouble with where the cameras are at a given point. Because right now we're going to have a look at the CAS. So all I'm going to do is define the function that we had there, not the simplified version of the function, but the actual function that we have. That's going to, well, not like that. Define, let's go, h of x is equal to 2x squared minus 5x plus 2 over x minus 2. Now with any luck, that wouldn't have simplified, kind of did. It's giving me a little warning sign here, and I'm pretty sure I know what that's going to say. Yeah, domain of the result might be larger than domain of the input. So what we're essentially seeing is that, yes, this fraction can be simplified into 2x minus 1, but when I go ahead and test h of 2, it gives me undefined. Because yes, even though it simplifies to 2x minus 1, the original function has a discontinuity at that spot. For that reason, we run into an issue. If I then plot that on a graph, right, we won't really see it on the CAS because the CAS isn't great at showing discontinuities. It'll just show the linear like normal. But yeah, all that to say, at x equals 2 specifically, we do not have an actual value there. The limit is different to the value of the function. The limit is 3. So if I go ahead and do limit again, menu for 4, limit x approaches 2 of function, limit is still 3, value is undefined. So in most cases, you are going to have this difference because otherwise there's no real point talking about limits. But if you're talking about any function that's like fully continuous anyway, then limit's pretty much always going to be the same as the value. Is it clear the difference between limits and values of the function? Some people get hung up on that a bit. Cool. All right. That's pretty much all we need to know about limits so far. There is a lot more to talk about for that particular topic, but that's for another lesson. All we need to know is enough to now move on to differentiation by first principles. So to start this off, we do a very simple revision, which is the so-called average rate of change. You guys all probably know this as rise over run, or, y2 take y1 on x2 take x1. All the same thing, they're all referring to the same equation. The reason why this is going to matter is because we're essentially going to adapt the average rate of change equation to eventually give you not the gradient over a domain of values, but the gradient at a specific point. So first things first, some fundamentals about average rate of change. You just need to know where you're starting, where you're ending, give the x values at those spots and the y values at those spots. This is fairly simple revision. So if you want to know the average rate of change between x equals 0 and x equals 2, then you need to give your x coordinate x1 as 0, x2 is going to be 2, and then the y values are going to be f of 2 and f of 0. Or you can just read them off the graph, of course, if you have a 2-scale graph. This is simply just rise over run. A bit more nuance to it. What you've essentially found is the average gradient over that interval. That's what rise over run does if you do it on a graph that isn't linear. Now, differentiation by first principles. The whole idea is to say, okay, cool. I want to know the gradient at specifically x equals 2. I don't care about all this other stuff behind. And so what I could do is say, instead of doing between 0 and 2, what if I did the gradient between 1 and 2? All right, that would be a little bit steeper, and it'll be a little bit closer to the actual gradient here. What if I take that even further? What if I do the gradient between, I don't know, let's call it 1.9 and 2? Well, if you imagine drawing a straight line connecting these two, again, the gradient's going to be quite similar to the slope at this spot. And so what differentiation by first principles does is it defines the gap between your points as a variable, and then uses a limit to set that gap equal to 0. Because when you have no gap, if you have like gradient of 2 points that are perfectly overlapping each other, you do get the gradient at that specific spot. To sort of highlight what's going on here, I've got a cubic. I pick a cubic because the numbers are a lot more larger to work with, so you can see the magnitude of what's really happening. So let's say I have a cubic. I want to find the gradient at x equals 10. Let's say I choose one x value either side of that. If I do my average rate of change, I'll get a gradient of 301. Decent approximation, not quite perfect. If I then get even closer, so now I'm 0.1 either side of the gradient, suddenly I get 300.01. Right? So I've knocked this like a couple of decimal places down. You can imagine that as you get closer and closer to x equals 10, we're getting closer to 300. We can see that that's where the pattern is tending towards. If you want to be a lot more mathematically sound, what you essentially do is you take your average rate of change equation and you just redefine terms a little bit. I said at the beginning of this section that what we're going to do is define a variable as the gap between the two points that we're using, which is why we're going to have delta x. The gap is just x2 minus x1. It's a difference of the x coordinates that we're looking at. Having defined this, we can do a bit of rearranging. So if we literally just rearrange this, what we can do is we can get a substitution for x2. Right, so instead of saying x2, we can now say what's on the left-hand side of that. So instead of saying f of x2, we now say f of x1 plus delta x. That's one thing we can do. The other thing we can do is instead of saying x2 minus x1, like we do here, we can replace that with delta x. This is just a bit of background as to where this formula comes from. So that gives you a rearranged version or a rewritten version of the average rate of change equation. What you do to make it the instantaneous rate of change equation is to stick a limit on it. We're trying to figure out what happens as that gap gets infinitely close to 0. That'll give us the gradient that we want. This is referred to as the instantaneous rate of change of the function because what it's doing is finding the gradient at a specific point, not over a domain. This is more so just for fun background. This isn't like accessible for you to prove the instantaneous rate of change equation. Just a bit of background as to where it came from. What you care about more will be, how do I actually use this thing? These are the steps you follow. You want to identify whatever the x value is that you have. Sometimes you won't even actually be given an x value, and you'll just have to use it as regular old x and rearrange from there. But most cases, you're given a specific value to work for. From there, you're going to simplify whatever expression you get, eventually removing your delta x, and then lastly, you're going to sub in your delta x equals 0. Because one of the problems with this equation, well, problem, is that if you just sub in delta x equals 0 directly, you get a divide by 0 error. All right, that's what we saw over here, where we sub in x equals 2, we got a divide by 0 error. Not good. So what we're going to do is now look at the actual example. We want to find the instantaneous rate of change of this function at x equals 10. So when we use our instantaneous rate of change equation, f of x plus delta x, well, f of x regular is just x cubed, and x is 10. So everywhere that you see x, you're going to replace with 10, and everywhere that you see f of x, or just f of something, you're going to stick a cube on that thing. So f of 10 plus delta x, because you have x equals 10, and then eventually that's going to come as 10 plus delta x, all cubed. Right, you're just subbing in 10 plus delta x in this spot. Same thing for this one here. F of x is just x equals 10, and so you're 10 cubed. That gets us our initial expression. A lot of the time, what you're doing when you're doing diff by first principles is you're expanding the numerator. Every single time that you expand your numerator all the way out, you'll notice that the constants will disappear. So you got minus 1,000 and plus 1,000. Those cancel into each other. From there, you'll notice that you're left with just the middle section. Each of these has a delta x. You can now cancel out that denominator, leaving you with just the 300 from here as the only thing that doesn't have a delta x left in it. You have no denominator now. We don't care that subbing in delta x equals 0 will break anything, right? We're safe to do that now. That'll get rid of these terms, giving us the 300 that we expected. Right, we kind of saw at the beginning that as we test these values, we get closer and closer to 300. Now we've proven it as mathematically as possible, or as mathematically sound as possible. That's the arithmetic. Is there any questions as to any part of that? I notice you've come off mute, but I can't actually hear any audio from that.
Nah, I don't
Oh.
really have a question.
Oh, sure. Okay. No worries then. Cool. Just a quick note on this. I don't think this will be... Oh, no, I think it will be relevant now, actually, because in this chapter they do... No, okay. It won't be relevant now, but it'll be relevant slightly later. What they essentially do is they use this equation for diff by first principles, but as soon as you hit year 12, or pretty much as soon as you exit this chapter, this doesn't get used anymore. This is unfortunately something that's tested in the Unit 1 and 2 methods, and then never again in Unit 3 and 4 methods. So if that looks like a headache, good news is you only have to do it once. So what they do from here instead is to say, okay, this was useful for limit math, but if we're not going to do limit math, then what we can do is we can say, all right, this whole numerator is just delta y, right? It's just a change in y values, your rise over run. And so let's just replace that whole thing with delta y, and then, you know what, let's just knock this whole limit thing off and just call this dy dx. All right, instead of using a delta, we're going to use a d. And so if you ever see this notation dy on dx, what you're being shown is the derivative of a function. This is the formal definition of derivative, instantaneous rate of change. This is it's still formal, but it's just another way of expressing this, typically used in the context of when you're using a table of values, a table of derivatives to look up. That's about it. That's all the lecture for today, basically. This one will probably be good for a breakout room approach. So what I'll do now is I'll chuck in the prescribed work for this one. It's going to contain the relevant questions that we've just covered. It basically bunches all of this 17A stuff into what are the relevant questions, or what are the similar questions, rather. Like for instance, you can see this one has a graph, this one has a point, this one has a point. It sort of breaks them down into what's similar, and so you can pick what questions within that group you want to do. And it also has a link to this particular book. So we're using the Unit 1 and 2 book for this one in particular. 17A, I believe, is the only thing on there. That's the prescribed stuff. I'll set up some breakout rooms. I'm not forcing you to do this stuff if you're not already doing it. So feel free to ask me pretty much any questions you have for anything that you're currently doing. I'll go around the breakout rooms and we'll take it from there. If there's any questions, let me know. Otherwise, when the breakout room thing prompt comes up, feel free to join it. That did not do it. Did it? Yep. Clicked the wrong button. Clicked the wrong button. Cool. Let's not do that one again. I gotta wait for 46 seconds apparently to have it not to let me do it again. Uh-oh. You'd think that would break the first time I do it, not the 50th time. Maybe that's what I get for being slightly faster at doing things. Any second now. It's weird that it puts it on a cooldown. I can't just force a breakout room to end. Okay, there we go. Let's fix this properly. Where is so recreate? Is that gonna be the button? Yes. Okay. This, that's better. All right, cool. Now everyone has individual break rooms. My apologies. Hey, sorry for the tech issue on that one. How's it been going so far?
Going all right.
Going all right? That's good. Do you have any questions in particular you'd like me to have a look at?
Not really.
Not particularly? Okay.
I'm still looking.
Yeah, no worries at all. So yeah, I guess just to more formalize what's going on here. I'll teach a particular thing at the start. We'll move on to breakout rooms, and the idea there is you either ask questions about what I've just covered or whatever you're particularly going on with. That's more or
Okay.
less the format.
Okay.
Cool. All right. I'll leave you to maybe have a think and have a play around with stuff, and then I'll circle back at some point later.
Okay.
Easy. Take care.
Yep.
I realize I forgot to check my Google form just in case anyone. Yeah, okay. No questions submitted ahead of time. Cool. I did not do a bad. Hey. How's it going?
Good.
Is there anything in particular you'd like me to have a look at?
Not exactly from this exercise, but I
Hmm.
wanted to just to have a little touch up on chain rule because I'm all right at chain ruling like one function. But then one day one of my friends decided to give me a question of chain rule,
Hmm.
which had like four functions or something, like four complex functions, and like it was like four different chain rules or something like that. And I really struggled on that. So
Yeah, no kidding. I mean, four chain rules is definitely four more, well, three more than is standard. And so That, it might be good. Do you have that question in
Yeah,
on hand?
let me check. Let me just find that real quick.
Sweet. That'll give me some time to make the camera stop crashing. So hopefully that'll that'll fix itself by the time we get there. Come on, assign, join. I gotta throw this phone out, man.
Is it really that
Apparently, but no, it's gonna join now. But sometimes it just fully crashes and it's like, no, I don't want to join.
okay.
Cool.
Let me see if I can find the question. I think I remember most of it.
Well, most of it's, yeah, okay.
No, no, no. Let me.
We'll get a very different result if you're even slightly off, but okay.
Okay, okay. I got it.
You got it?
The question was, so natural log,
Yeah.
then a bracket, sec squared. So I'm guessing
Oh
1 over cos
God.
squared.
Yeah. Okay.
And
Yep.
then bracket e to the power of x on 2.
Oh, okay. That's only two chain rules then. That's not the end of the world then, maybe. This is all cameras good.
Let me check that. Yeah.
Cool. All right. So first step was probably the easiest for you, which was defining u as the brackets. So just going full tilt sec squared e x on 2. Therefore, you've got y of u is equal to natural log u. That's a fairly chill starting point.
Yeah.
Okay. Um, Next easiest thing, of course, is going to be just doing y dash is equal to 1 on u. So that's not so bad. This is where we start getting into issues because now, um, yeah, so doing 1 on cos squared is a good start for this. So converting that to 1 over cos squared ex on 2. That's good. And now diffing this. Um, let's use negative indexes instead.
I thought e to the power of x on 2 would be still above the fraction. Okay, let me
No, so it goes whatever's. I'll show it, I guess.
all right, because it's in the brackets here. Never mind.
Yeah. Okay.
Got you.
Yes, that would stay there. So let's use negative indexes for that. Oh, this will be a third set of chain rules because you got cos negative 2. Because the next thing, so let's call this where are we going to put this? V, I guess. V is going to be cos e x on 2 because that's the next like smallest, or sorry, the next biggest layer that we can now chunk down. Because when you now write u of v, you now just have v to the power of negative 2, right? Because cos power of negative 2, v power of negative 2. Okay,
Yeah.
this one's pretty chill now. U dash v equals negative 2 v negative 3. Let's fix that negative 2 so it doesn't look like shit. 2. And now for this diff, once again, you've got a chain rule, although you might be able to do this in your head. But if you don't, that's fine. We can just do another chain rule from here. So basically, we're looking for v dash. So uv x. We already kind of used x. Let's just use a now. We'll circle back. So a equals e x on 2. Probably should have put that below further. A equals e to the x on 2. And so v of a is therefore cos a. V dash a is equal to, so cos becomes negative sine a. And then this one's not bad at all. So a dash is equal to half e x on 2. All this is cool so far?
Yeah.
Okay, cool. So now to do our proper chain rule, so d dv on du. Hang on. Now here's the fun bit to try and actually unwrap this. So this is y. In order to get, to clarify our thinking a bit, we can say in order to get dy on dx, I needed du dx and dy du. So du on dx times dy on du. We have dy on du already. That was 1 over u, which we'll put in later. So we now just care about du on dx times 1 on u. Now, the next thing that's missing is du on dx. How do we do that? Well, to get du on dx, we need this thing here. So derivative of this is dv on dx times du on dv. Yes. dv on d... no, du... In order to get du on dx, we need to do dv dx du dv. dv dx du dv. dv's cancel, that makes du dx. Okay, cool. So the challenge in this is not the actual execution, it's the tracking of variables is the pain. And even though this is still tough, it's probably the only way that I can imagine really keeping track of everything. Now, one of these we're going to already know. I think that's du dv, which is negative 2 v negative 3. So dv on dx times negative 2 v negative 3
over u.
Yeah, correct. Now, this is probably where it ends. dv dx is dA dx over dv dA. So dA dx dv dA. And then, all of this will be there. dv dA, that's supposed to be an A, is negative sine A. And so now you just have negative sine A times all of that, and dA dx we have as well, right, which is this, the half e x on 2. So again, half e x on 2. That's our final dy on dx. So I could go ahead and then sub in your u value. What even? Yeah, that's actually an A for that one. That's just me being bad. That had an A in it. That had a V in it. That had a U in it. You would then just go through and then sub in what you know the A, U, and V to become, and that'll get you your answer. That's a grind for sure. What are your thoughts on that?
A pretty mouthful of question.
Yeah, I mean, look, if you can follow that and achieve that, then you're already like 2 steps ahead. Like this is like if you think about like normal distribution stuff, let's let's estimate where you're currently at. You're at like the 4th standard deviation of doing chain rules for methods. This will never come up in methods.
Yeah, I don't know doing an exam because it just doesn't make sense to waste so much time. Like,
yeah, this
that was
won't be there.
5 minutes. I
Yeah.
think.
Say again.
I think that would take like a minimum 5 minutes in like an exam.
Yeah, this will take a while. Like this got us the expression. Subbing the rest of these in, I don't know. Does it say when I join the breakout room? It wouldn't have been. Maybe it's been about 5 minutes. Yeah. But yeah, so if for whatever reason you're like pushing yourself to do this sort of stuff, then sort of breaking down the working out into little sections like this that you can then easily see what all your terms are. Maybe even be super consistent with the wording and use the fraction notation just so it's easier to see what's what. Getting away with just saying dashes is really easy for typical chain rule stuff, but obviously if you're going to now stack it 3 times on itself, then, well, you might want to start really getting good. Like, look at this mess.
Yeah,
um,
yeah,
but yeah, trying to unwind it. Usually we're pretty happy with just subbing things directly in because it's a one-liner. Because you had to break down the fraction 3 separate times, breaking it down like this step by step really can help clarify your thinking. And I'm hoping you at least see that based on the fact that you maybe understand what I've got written here.
yeah.
Understanding the approach well enough?
Yeah, got you.
Awesome. All right, that's that one. I'll circle around a bit more, and if you have another fun question for me, I'll be sure to tackle it. This will be really funny for someone to see as the first thing when I join their breakout room, by the way.
Yeah,
All right, take care.
thank you. See ya.
See ya. Hello. How's it going, Pia?
Good, how are you?
I'm doing good. I'm curious to hear how you've been going. If there's anything you want me to have a look at.
Yes, there's a question that I need help with.
Let's do it. Whereabouts is this question?
It's in the 3-4 book. It's from 15A, I think.
3-4
Um,
book 15A.
and example 3.
3-4 book 15A. Example 3. Like a literal example or question 3.
Example.
Example. Okay. Let me pull up the screen share for this. Okay. 15A. Example 3. Whereabouts was this one?
Yeah, part B.
Part B. Show that's a probability density function. You can ignore what f of x even says. There's only ever one thing you do here. Do you remember what that is?
Is it that it has to equal 1?
Yes. More specifically, the integral over the maximal domain has to equal 1. And so that's where we start. So our goal is going to be to integrate our function over its maximal domain. Okay. So what is the maximal domain of this function that we have?
X has to be greater than 0.
Yep. And so what does that mean for the terminals of our integral?
Infinity to 0.
Infinity to 0. Yes, correct. Yeah, infinity on top, 0 on bottom. That's it. Cool. And so it's subbing in infinity that's probably the issue for you, is it?
Yeah.
Okay, cool. So this is actually pretty topical then, because we did look at limits. What happens as a function approaches to infinity was one of the things I did not cover because it wasn't going to be relevant to at least that portion of the lecture. And so it's probably now that we can now have a bit more of an exploration into that because it will be relevant to the substitution in here. Basically put, if you have infinity as just a value in a line, like if I have like 2 plus infinity, for instance, obviously dumb example, but that's going to equal infinity. However, because infinity is an infinitely big thing, if I have it in a denominator of any sort, that term basically just goes to 0, right? You have a massive denominator, the term basically disappears. So when I have something like 2 plus 1 over x and x equals infinity, I have that approach. Even further, when I rewrite that as a negative index and x goes to infinity, I also have that thing. And so one of the things you'll one of the things you'll have when you anti-diff this is you'll have a negative index, right? E to the power of negative something. When you put an infinity in that spot, that's the same thing as cancelling out the entire term because it's in a denominator now, not a numerator. So that'll be the main concept to consider for that. Is it fair enough, at least conceptually at the start, what's going on?
Yeah.
Okay, cool. So, anti-diffing this. How are we going to do it? Capital F of x.
Would it be that over -2?
All this divided by -2. Yep, sounds about right. So we're looking at capital F of x equals negative e negative 2x. Let me just double check. If you diff this, becomes 2e2x. Yes, it will. Cool. All right, that's good. What do we do now to complete the definite integral?
We have to sub in the upper and lower bound.
Up in the upper and lower bound, correct. Yeah. So capital F of infinity minus capital F of 0. And remember, we already know the value ahead of time is going to equal to 1. So now that we go through it all, negative e negative 2 infinity minus capital F of, sorry, I shouldn't do capital F for that one, minus bracket negative e negative 2 bracket 0. That's going to equal 1. Oh, it's just proving actually. Let me have a look. What was going on? Yeah, prove it, not solve. Okay. So making it equal 1 ahead of time, it'll equal 1 anyway. But anyway, so this one's the easiest to consider. Negative and negative makes positive, and then e to the 0 is what?
1.
Yeah, e to the 0 is 1, so we have a positive 1 on this side. And then this, maybe to even drive it home a bit better, any negative index, so 2 times infinity is still just going to be infinity. And so what we end up having is negative 1 on e to the infinity. All right, that's converting our negative index into a positive index. Whenever you have something that is infinitely big in the denominator, you know, because e is roughly 2.7. 2.7 to the power of infinity is basically infinity. And so that term cancels out. 1 equals 1. We've now proven that we have a probability density function. Is that cool?
Yeah, that makes sense because the way they did it was like, I didn't get it because they made the limit and then they made like k.
Yeah. Yeah. Because like what I'm doing is technically you shouldn't be subbing in infinity pretty much ever. You should technically be finding the limit as k approaches infinity because you can't sub in infinity. And so they're putting a limit in there because that's technically mathematically required. However, what exactly are they doing with it? They say 0 to infinity. Oh, did I? Wait, what? Oh no, we did it in the right order. Yeah, I just blanked for a second there. Oh yeah, okay. So what they're basically saying is instead of having infinity as a terminal, because infinity is not a number, you can't really do that. They say, okay, let's put k up there and then say what happens as k goes to infinity. So fundamentally, it's the same working, but they're using limits because it is more mathematically accurate. You're not going to ever lose a mark on this if you just go straight to chucking in infinities there. Like even the CAS won't care about that. The CAS isn't going to expect you to put a limit for k on the thing. It's just going to be like, yep, if I'm doing 0 to infinity of, I guess even e to the x, or e to the negative x rather, it'll give me a value, right? Like it's not gonna say, hey, you've done something stupid, don't do that. And so, yeah, that's why that's there. Cool.
Yes, thank you.
No worries at all. Anything else you want me to have a look at?
Could we also do C?
Also do C, yeah. Find probability x is greater than 1. That's a very stock standard question for continuous. So anytime you want to find a range of probabilities, do you remember what you do to find like a particular range of probabilities?
Do we just anti-diff it again
Yep. Antidiff
and
is part of it.
change like the lower and upper bound?
Exactly. Yeah. What are we going to change them to?
Would we just change the lower bound to 1?
Exactly what you do. Yeah. So if we have a look at this, they put this whole limit shit around it. Just pretend it says infinity there and ignore the limit. There's your antidiff, like we did from before. There's a simplified antidiff. This is just doing capital F of infinity minus capital F of 1. And because, you're putting a 1 in this spot, oh, sorry, this spot, I guess. That's why you got the -2 there. And so from there, what's happening is this is an infinity in a negative index, which is why that whole thing will disappear. Negative, negative makes the positive there. And then, well, you've just got e to power -2. Does this need to be expanded at all, or are you happy enough with how that's now?
No, it's all good.
That's all good. Easy. All right, cool. Yeah, that was a quick fire one. Was there anything else you wanted to have a look at?
Could we just go over like the basics of conditional? Because I'm still like when
Hmm.
finding the intersection on the numerator, like that gets me a little bit.
Yep. Okay. So for basics of conditional, here it is. We've got between 8 and 10 seconds, given that it takes less than 12 seconds. So first thing you want to do is identify the two domains that are being expressed. So in this case, the numbers that we care about are 8, 10, and 12. And so I'll always just put them on a number line. 8, 10, 12. The first domain is between 8 and 10. So let's draw a thing connecting those. The second domain is less than 12. So let's use... When it's continuous, you don't care about dark circles versus open circles because we don't jump immediately from 11 to 12, for instance. We jump to 11.999 recurring. And so whether you use a dark circle or an open circle is whatever. So those are our two things. Those are the two domains. Is it clear enough how we got those?
Yeah.
Okay. Now here's the easy bit. All you do is you look at where they overlap. And so the final answer for the intersection of the two domains is just going to simplify down to just 8 to 10. So in this case, it is a perfect match. If this one had cut off earlier, like let's say it cuts off at 9, then all of a sudden your intersection is now from 9 to 10 instead of 8 to 9. You just look at where they vertically overlap, and that's your entire top bit. Make more sense?
Yeah.
Cool. Was that the only part left of conditional probability that needed explaining?
Yeah.
Easy. All right, I think I'll leave that one there, and yeah, I'll continue doing the rounds. I'll leave you to it. Hey, hey, just checking in again. Yeah, how are you going with the work?
I have a question.
Yeah. Okay, let's hear it.
So question, it says to simplify sine theta plus cos theta. Wait, is that okay? No, wait. Sine. Yeah.
Sine squared plus cos squared, or just sine and cos?
Chapter 15,
Chapter 15. Is this unit 1 and 2 or unit 3 and 4?
unit 1 and 2.
Unit 1 and 2, chapter 15.
16a.
Chapter 15, and it's 16a. Okay. Chapter 15. Sorry, chapter 15 what?
16a.
Oh, 16a. Okay. Yeah. This one?
Yeah.
Simplify sine and cos, whereabouts?
No. Chapter 15, like, it's revision.
Chapter 15 revision. Okay, and it's 16A of Chapter 15 revision.
Yeah. 15B.
15B. This one.
Yeah.
Okay, got it. These are symmetry property things. So what's going on here is I'll pull up my notes for this one to explain them. Pretty much all of the symmetry properties can be explained with what I refer to as a first quadrant reference angle. That's a fancy name for basically just drawing a unit circle and then drawing a line off of that unit circle. I'll show you what that looks like in a second. Symmetry, and where specifically, well, I'll just show you a fundamental one. So basically what you do is to sort these ones out, at least it's a nice like visual way of doing things. You draw a unit circle and then whatever value you know, whatever you have, is going to go somewhere in the first quadrant. Then from there, whatever thing you're trying to simplify, you then do a certain thing to reflect it or shift it somewhere else into some new quadrant. Now, a bit more challenging for this because you don't have specific values for them, but you can still make use of the overall concept. So for instance, both of these say pi plus theta. So we're going to go to the section where you have pi plus theta. That's going to be, either of these sections. We care about sine and cos. Now, technically speaking, the fastest way to do this is just to know that whenever you have pi plus theta, sine becomes negative. Whenever you have pi plus theta, cos also becomes negative. And so, the easiest way to go about this is to just know that this is going to go to this, because pi plus theta always makes them negative. That's tough to have memorized because this doesn't go on your unit circle. Oh, sorry, it doesn't go on your formula sheet, and this is a lot. Like if I scroll all the way to the bottom of this, like this is all the stuff that gets covered. That's a lot, yeah. And so what you can do to make life easier is actually bunch a lot of these up. Like all three of these are talking about the exact same thing, and I'll show you what that is. So pi plus theta just means that you start at some location, right? So you have some initial value. Pi plus theta means, or basically put, whenever you have something plus theta or something minus theta, whatever that something is your new starting location on the unit circle. This is pi, so we start at pi. Cool so far?
Yeah.
Now, plus theta means that basically whatever angle got you started over here is now going to continue on in the same direction over here. If you have a value, the values will matter. In this case, we don't have a value that we're looking with. So what we end up caring is the sign, whether it's negative or positive in that particular quadrant. And so because pi plus theta will always put you in third quadrant, whatever you started with will be multiplied by a negative. If you started up here, it's positive, it's now negative. If you started down here, you would flip up here, you multiply by -1. And so that's why any pi plus theta will cause sine or cos to go negative.
Okay.
Is that a better explanation than just looking at this?
Yeah.
Yeah, okay. I had a feeling. Because, you got basically two options, which is use the same approach, so use this whole unit circle stuff for all of them, or memorize, how many got? 2, 4, 6, 8, yeah, a lot of things. Or, that's one group there. This is one group here. There's another group there. One group, one group, one group. So a lot less to actually memorize. I forget, did you grab this bundle?
Nope.
Yeah, okay. So here's a demo of what that's like if you're interested in having that. This is the kind of stuff that you can have access to. Or obviously you just sort of watch these recordings, and as they become relevant, you'll see them in the recordings. These will show up in the past recordings section of the classroom. Have you had a browse of that yet?
Nope.
Yeah, okay. That's open to you already, just because you're part of this program. You get to see the class recordings. So, if you're on a budget, then you can obviously see them as appeared in the video. It's
Okay.
a yeah, it's a bit harder obviously than just having it, but yeah. And so okay, yeah, that's why we're going to end up with this as the answer. Is that cool?
Yeah, yeah. Okay.
Awesome. Yeah, we've got a bit of time left. Was there anything else you wanted to have a look at?
Mm. Can you like explain to me like the translation of sine and cos? Like it moves like up and down and
Mm,
left and right. Like
yeah, yeah, certainly. So let's pull up the notes on that one. Sketching sine and cos. So the way it works is identical to the way quadratics work. Are you familiar with the transformations for quadratics?
yeah.
Okay, cool. So whenever you have, in quadratics, you'd have x minus something would mean going to the right, and x plus something would mean going to the left. Exact same thing in circular functions. In quadratics, whenever you had a plus at the front, or I guess at the back, it will go up, and whenever you had a minus, it would go down. Exact same thing with circular functions. Also, exact same thing across every function. Whenever you have x minus h anywhere, that's always a shift right. Same thing with the plus c. So those are like fundamentals around the transformations. If you're looking to get a bit more detail as to what that means for the circular functions, horizontal translation, when you're sketching things at the horizontal translation, what that does is it essentially tells you your new starting point of where you're drawing it. Because normally you would have it start at the origin and then go, whether it's sine or cos, it'll go up or down at different values. Whatever your horizontal translation is, shifts that initial starting point. So instead of starting at 0, we start at pi over 2 now, because it's shifted right by pi over 2. Where you see it starts like here now. Is that fair enough?
Yeah.
Okay. And then when it comes to vertical translations, sometimes you love them because vertical translations means it doesn't even bother touching the x-axis, and so you don't have to find anything new. You just the easiest way to explain a vertical translation is that it sets the middle line of the circular function.
Okay.
So normally they start at 0, right? They're dead center. They go up and then down from the center. Now we have a plus 2, so the center is now y equals 2. Now we have a minus half, so the center is now minus a half, right? That's how that one works. As for what you now have to consider, if you have a sufficiently annoying vertical translation, you now have to find your x-intercepts in addition to your other key features. And that makes it a bit painful. All you're doing is subbing in x equals 0 and y equals 0, though. It's work, but it's not anything you haven't done before. It'd be like a chapter, whereabouts is it? It'll be in this, I guess. It will be like chapter 14, where you're solving the circular functions. That's sketching. That's also sketching. It'll be like G.
Okay.
So were you cool enough with doing the stuff in G?
Well, I already know to do like I already know how to do G, but like
Mm.
do you know like how do you find the points when you sketch it? It's like 2A, 14J. That's kind of hard. I struggled.
To a well, 14J isn't sketching.
I mean 14I.
Yeah, okay. 2A of this, sketch the graph, linear axis intercept. Yeah, so that'll be, we're about to end the class, so what I'll do is I'll drop this one in there, and you'll need to read up on, okay, this is vertical translation, so read up on, is it this one? That's the actual example. Yeah, read up on, where is it actually located? Vertical translations, vertical translation C. This example here will walk you through the steps that you follow for that particular thing. So I'll give that one for you. You can just have that. I'll just send it in the everyone chat. Why not? And yeah, I think that'll do that. So let me know via text how you go with that.
Okay.
And if you like this sort of stuff, well, that's what's that's what's on offer. Cool. All right, I'll close these breakout rooms real quick, and then we'll just end it here. The recording will be live in a couple of days or so on the thing if you want to watch these back.
So
Cool. All right. Oh, I default mute myself. How interesting. Thought I always had mine set to not be muted. Anyway, lesson's obviously over. If there's anything you want me to clarify, I'll be here to stick around for a little bit. Otherwise, I'll leave you to it.
Thank you.
No worries.